Thank you, Zukin, for hosting with us. And I'm looking forward to today's webinar. It's an important topic to everybody, all designers. And please ask some difficult questions. You know, we have Lance, technical expert, on the call. We also have PCB engineers on the call. So as always, please hit us up for your difficult and most challenging questions. With that, I'll get started. So if you don't know Sierra Circuits, we're a PCB manufacturer and assembler in the Silicon Valley, and we cater to all the businesses around here, as well as throughout the United States, ranging from military aero to, you know, industrial and consumer. Here's the TOC. And really want to start off with just the basics. So why decoupling capacitors? So decoupling capacitors are essential for filtering high frequency noise and ensuring a stable power supply to your ICs. You know, these capacitors will dampen the high frequency resonances and minimize unwanted parasitic oscillations in your power supply lines. So these, moreover, will ensure smooth signal transmission by reducing EMI and crosstalk between adjacent traces. And then another vital function of decaps is maintaining a steady voltage level by providing a local energy reservoir. So when your circuit demands a sudden surge of power, you know, these capacitors can supply the necessary, you know, charge, keeping your voltage stable. And then lastly, decoupling capacitors prevent power supply variations in one section, which, you know, may affect another section. These are all very critical points to your PCB functioning properly. So we're going to start off talking about local decoupling capacitors and their importance. So these small capacitors are typically placed close to the IC's power pin. The typical values of these capacitors range from 0.01 to 0.1 microfarad, and one of the primary purposes of local decoupling capacitors is noise reduction. So these capacitors will filter out high-frequency noise generated by the IC's fast switching activities. And additionally, these capacitors help minimize parasitic inductance in the power delivery network. Then we have the bulk decoupling capacitors, which are larger capacitors generally placed on the power distribution network, or PDN. And depending on your circuit's power requirements, the typical values of bulk decoupling capacitors range from 10 to several hundred microfarads. And one of the primary purposes of bulk decoupling capacitors is to maintain overall voltage stability across the entire you know, circuit board. And these capacitors can can supply transient charge when needed, ensuring the voltage remains stable even during sudden changes in the load. So bulk decoupling capacitors filter low frequency noise and transients that smaller local decoupling capacitors cannot manage. So we have a new tool, PDN analyzer, you know, which is free to everybody. And I think we're going to do a demo of that. Is that right, Lucy?
Yes, Vandana is here. She's going to do the demo.
Okay, I'll stop sharing.
Yes. Thank you, sir. So Sierra Circuit's power distribution network analyzer determines the target impedance, fastest rise time, and the maximum frequency here for a PDN based on the power rail voltage, maximum power rail current, and the acceptable voltage ripple, and also the switching current here. To use the calculator, we enter the power rail voltage. Let's go for 3.5 volts for now. Let's change the acceptable voltage ripple to 2.5%. we enter 1 ampere for the maximum power rail current and 80% of I max of switching current. Now we can click on calculate. This displays the target impedance here. You can calculate the maximum frequency by changing the fastest rise time if you wish to, and then click on calculate. Or you can also use this drop down here to calculate the fastest rise time for a given maximum frequency. Click on the save to table button here, and the calculated power rail will be saved in the button in the table below. You can export this to Excel too, and you can start your calculations for a new power rail. The power network in your circuit board layout should ensure stable power delivery. So high switching speeds can lead to voltage fluctuations, crosstalk, and EMI in the system and hinder the performance and the reliability of PCB. These challenges can overcome by maintaining a power supply's AC impedance below a target impedance. And our tool helps you to optimize the power delivery network in your PCB layout. Thank you.
Thank you. Can you guys see my screen?
Yes.
Okay, great. So as always, ask questions. I think we'll probably save the answers to the end, and if the webinar goes over a little bit, I think that's okay. We have some good demos from Zukin later. So placing decaps, to achieve power integrity. So first we'll talk about placing decaps without power planes. So place at least one local decoupling capacitor between IC's voltage and ground pins. This placement will help to filter noise and provides a stable power supply to the IC. Use capacitors with nominal values. As such, maintain a small loop area between the capacitors and active devices. Add 2 local decoupling capacitors of the same value instead of one with double the value. This can help reduce overall inductance and improve filtering efficiency. And position both decoupling capacitors near the power supply to ensure overall voltage stability. These capacitors act as reservoirs, as we were talking about, providing charge during transient events and maintaining a stable voltage. The values for bulk decoupling capacitors should be 2 to 10 times the local decoupling capacitors on the same voltage bus, and this ensures the bulk capacitors can effectively support the local capacitors to maintain voltage stability. So next we'll talk about placing decaps with broadly spaced power planes. The loop inductance can significantly affect circuit performance when the power planes are spaced more than 0.5 mm apart, or roughly 20 mils. To mitigate this, place capacitors close to the IC's power and ground pins. This proximity helps reduce the loop inductance and improves the capacitor's effectiveness. So do not add vias between decoupling capacitors and an active device when they are located on the opposite sides of the board. Avoid traces between capacitor pads and vias. Position vias directly on the mounting pads. Place the capacitor as close as possible to the power pin and connect the ground pin to the ground plane using a via. So next we'll talk about decap placement on PCBs with closely spaced power planes. Use capacitors with higher self-resonant frequency for closely spaced power planes, specifically those that are 0.5 mm or less apart. Higher SRF capacitors can better handle high frequency noise. Use polygons over traces for bulk capacitor connection to power ground planes. Place vias on the capacitor mounting pad. If placing vias on the capacitor pad isn't feasible, the next best option is to position the capacitor as close to the via as possible. This reduces the parasitic inductance and resistance, maintaining low impedance in the connection. For local decoupling capacitors, always mount them near the power and ground pins of the ICs. This placement minimizes the connection inductance between the capacitor and the IC. It's also essential to have dedicated vias between decoupling capacitors and the IC. Shared vias can introduce additional inductance and reduce the effectiveness of the capacitors. Use multiple decaps of the same value near the power supply for high-speed circuits. If not possible, the lowest value capacitor should be closest to the power supply as shown in the image. So here we have 6 guidelines for placing the decaps for signal integrity. So to reduce parasitic inductance and capacitance, place the decoupling capacitor directly beneath the IC's power pin or right next to the pin. Employ capacitors of similar values in parallel to cover a broad frequency range. Ensure each power supply rail has its decaps, as different power rails may have different noise characteristics and current demands. For multi-layer boards, use multiple vias to connect the decoupling capacitor pads with the power and ground planes. This approach minimizes the loop area and reduces via inductance. Place decoupling capacitors directly into the power plane through short vias to avoid trace stubs. Connect the component pin to the capacitor first and then to the via ensures the shortest current path for noise filtering. I think we're going to do a quick impedance tool demo as well. Can I go ahead, Vandana?
Yes. We have the impedance calculator here, which uses the 2D numerical solution of Maxwell's equation for PCB transmission lines and renders a fairly accurate result suitable for the circuit board calculations. The impedance calculator tool supports 82 models, impedance models with multiple geometries, like the uncoated, coated, embedded in strip line here. And each of these model can be paired with a single-ended differential pair or coplanar over here. The tool is also integrated with the signal loss, crosstalk, and the S parameter calculator. Let us start with a coated microstrip in a differential pair. The simple and the composite calculator is shown here. Let's go with the simple one for now. Here, you can use any unit system here. Let's go with mils for now and enter the inputs. The dielectric height of about 3.348 mils. The dielectric constant 3.63. Coating height H1C is 1.5. H2C 0.5 and H3C is 1.5 again. Let coating dielectric constant here 2 be 4.2. We'll enter a value of delta W here. Delta W is the difference between the top of the trace and the bottom of the trace. You can click on the help content here for a table that suggests delta W values based on the starting copper weight. Let's go with 0.5 mils for now. Enter trace thickness by clicking on this plus sign here. And there is a list which appears and you can choose the copper thickness and the trace thickness will be updated automatically. Now you can enter target differential impedance to calculate the trace width. Let's go with 100 ohms and click on calculate W. So we can see that, sorry, I forgot to add a trace separation. Go with 1.4, 2.2 for now and calculate click on calculate W. We can see that the values are calculated here. Similarly, you can calculate the target differential impedance by entering a trace width here. Let's go for the signal loss calculator. Enter a dissipation factor of about 0.025 or 24, and then a frequency of 10 gigahertz, a surface roughness of 6 micron, because that's a standard for a foil, and let's go with 2 inches and click on calculate loss. We can see that the signal loss in the signal loss output for the odd mode and the even mode are calculated and displayed here. Similarly, you can use the S parameter and the crosstalk calculator for the chosen geometry. Thank you.
Thanks, Vandana. me share my screen again. You guys see it okay?
Yes.
Okay, great. So we have some guidelines to mount decaps in fine pitch BGAs. So obviously this is not every possibility, but we thought we'd touch on the topic a little bit. But definitely ask questions, and if you need specific examples, we can always follow up after the webinar as well. So really this is to start the conversation, and if you have questions, we'd be happy to address them offline as well. So, some guidelines to mount decaps in fine pitch BGAs. So you want to optimize the decoupling effectiveness. So place decoupling capacitor directly under the BGA to shorten the distance to the IC's power pins. This placement minimizes the inductance and provides a more direct power delivery to the IC. You can also put capacitors between two BGA rows when space permits to reduce loop inductance. And another effective strategy is to position capacitors on the opposite side of the board, aligned across the periphery of the BGA. And this arrangement allows for efficient use of space and minimizes the distance between the capacitors and the power pins. You want to align the capacitors so that the BGA fan-out vias can also be used to connect the decaps, and this orientation minimizes the inductance and saves space for signal routing. And lastly, you can implement VN pad technology to connect capacitors directly to the BGA power pins, ensuring a low inductance path for power delivery. And then, what are some quick tips for decoupling capacitor placement on your PCB design? So you want to choose a capacitor package size that your assembly shop can easily place, but also inspect too. So both placement and inspection need to be considered. And then of course, assess what size you would need in order to properly design your board with the right spacings. And ensure the capacitor can handle your circuit's operating temperature range. Select a capacitor with a voltage rating higher than the maximum circuit voltage. Use multiple capacitors to cover a broad frequency spectrum and ensure effective decoupling. Choose capacitors with low ESR and ESL for high frequency decoupling to reduce power loss and improve transient response. And always refer to the capacitor data sheet for detailed specs. Sierra has created a BOM building tool which incorporates a lot of these tips. And I'm not sure if we're demoing the BOM building tool today. Vandana, are we doing that?
We can do the demo today.
Okay, yeah, I think that would be nice to show that. And maybe now's a good time.
Yeah, sure.
Okay, great. Yeah, it's a new tool. Again, the tool is for our customers and people who are not our customers as well, to just try it out and see if it helps and assists in your design process. And then just, as a side note, it's a new tool, so whatever improvements you'd like to see or what you think would be more helpful, we're open to those suggestions. By new
Yes.
tool, I mean it's in beta.
Okay, so we have the BOM builder tool here. It facilitates the process of creating an accurate and error-free bill of materials. The tool also has a built-in component selection tool to ensure manufacturability. So here we have two options. We can either click on this button here and create a new BOM from scratch, or we can upload an existing BOM. Let's do that first today. Let's go with this. And then click on upload. You can also download a sample BOM there. So this column mapping section here, it's basically over here to map all the columns from your Excel sheet to the titles on the left here, just to avoid confusion, and then click on proceed. So once you proceed, the BOM validation process is already started, and once it's done, the label here will change, and we can see that the issues over here are highlighted in red. We also have suggested Sierra preferred parts over here as an alternate option. So you can replace those existing parts with the alternate over here. And the data sheet and the product URL of each of those components are also provided. So now it's replaced. You can also delete any component if you wish to, or you can also compare desired components by clicking on these tick boxes here and clicking on compare selected. So we can see that there is a side-by-side comparison of the specifications of the components. You can also add a new component here by clicking on add new button. So over here, there are two options. Either you can enter the quantity per board, manufacturer, part number, and reference designators. Either way, you have to do that. But in case you don't know the manufacturer part number, you want to choose a new component, then you can scroll down here to the component selection tool and select any of these components here. And then use these drop downs for your specifications. And then click on apply filter. So you can see that there is a table of all the components will be displayed over here with their data sheets, product URLs, footprints also. You can click on this add to favorite button, and then these components will be saved to a my favorites list. So this list help you with easy to access easily the components that you will be using in future. So let's take this component for now, for example. Then I can add in the quantity per board, manufacturer part number, and the reference designator, for example. Validate it and then save it to, and it will be saved in the table. You can click on the save bomb to save this bomb for future this thing to continue editing it in the future, or you can click on export to Excel and download the bomb in this Excel file. You can click on the saved bomb list over here, and the table will be shown where you can where all the previously saved bombs will be visible, and you can click on edit to go to that particular bomb and continue editing again. Thank you.
Yeah, thanks, Vandana. And again, to the community, this tool is really built for you guys, and then for any existing customers. We're integrating it with our back end manufacturing process. So our inventory will have all the preferred parts, and our machines will be set up to inspect and place the preferred parts. So the goal is to lower cost for you and for us, and to be able to ship things faster. So I'm really excited about that tool. We did ask a friend, Steve Sandler, a known expert in the industry, about decoupling capacitors and how they minimize voltage ripple. And so you can see his answer here. Also, here are some examples of decoupling capacitors and their ranges and benefits. And with that, I'll hand it over. Thank you guys. Thank you very much. Lance, would you like to continue?
Yeah, sure. Let me share. You guys can see my screen, right? Oh, Lucy, should we have a poll question again?
Oh, yes, right. Thank you so much for reminding me. Okay, so quick poll, only 2 questions. And go. Okay, thank you so much. You can get started, Lance.
Okay. Are you gonna show the result? I was interested.
Oh, sorry, no, I already closed it.
Okay, that's fine. All right, so thank you, Amit, and your presentation was great to talk about the decoupling capacitor for our power delivery network designs. So what I gotta talk about today is every circuit design engineers need to understand what's the decoupling capacitor concepts right there, right? So when you have those knowledges, when you can design the power delivery network more robust. And we also need to, well, after we design, we also needed to verify if our design has a problem or something didn't catch, some problem didn't catch, or what's the optimum selections for it. So that's what the power integrity analysis tools come in place. Of course, the last measure, the validation is physical measurements. So before that, basically, we needed to use the power integrity analysis tools for design verifications or design debugging, plus design optimizations or what if scenarios. So optimization, what if scenarios is also very important because sometimes you really want to reduce your cost. If you have a high volume product you need to manufacture, you really like to be optimized. Take off one or two decaps is also make huge difference, maybe a couple of $1 million, even more. So Zuken CR8000 products is basically enables those verifications, debugging, and the optimization for your PDN design. Of course, Zuken tools in general is we have a built-in simulation analysis environment for high-speed PCB designs. It combines time domain, frequency domain, TDR, and eye diagram analysis from schematic circuit design all the way to the complete 3D PCB design, system design. So it's not only we have a built-in tools, we also can seamlessly connect to some top-tier analysis tools like ANSYS, the Keysight, those guys for simulations as well. Yeah, so it's very, very fast. So that's what I have one of the webinars, past webinars talking about EMC SIPI screening, which is you can scan that code, go to Zuken's website to watch that again. So these are, we're talking about not only the PI, not only the SI, but both for the high-speed design screening process. So today, it's basically, I'm focusing on the decap analysis and the optimization part. So when you have a PCB design, it's automatically the tools will automatically recognition the decaps for you, whatever it's cross the power and the ground buses. So if you see, this is the pictures the tool has. So there's a specific PI decap, and so you can click that, automatically list that for you. So these are actually listed all the information for you because we have the footprint, we have the specifications saved in the both layout design systems, so everything can be calculated, pre-calculated. So when you click, it's just you can see all the things there. So like important stuff is like ESR, ESL, like Amit was talking about, right? So these are all can do that automatically for you. So also we will calculate the partial loop inductance, the resonance, and the bandwidth, those and the Q values, which is Steve was talking about in Amit's slides there too. So we can do that. So we also have a simplified displays for power bus. So the board could be very complicated, right? So, but since we're focusing the power and the ground plane, we actually can be easily just display those. So make sure people can be easily spot the problems. You need to pay attention to it. So also, when you zoom in, you actually can see those footprints in details, but it's kind of like a simplified way. This is like a true real layout look like, but this is the power bus look like. So you basically can be easily to find out how that goes. If you think this need to be changed, that will be easy to do. So one thing is it's very easy for optimization or verifications is that we actually have a capability to toggle on and off for select the decap capacitors. So let me go back. See, if you see this is the check mark there, which is all select. So everything is on. So you could be take something off. For example, in this case, I deselect the CA41 all the way to A44 and also the CA48. So basically, if you see the AC input impedance color mapping display, this is like a scale from 0 to 1. Anything above 1 will be red. Okay, that's what the color mapping for. So this is basically the all lower than the 1 for this power ground pair. So if you deselect those decaps, so automatically you can see the somewhere is actually violating this settings, right? So it's basically you can see this says that the 1.3 is the highest one in this mapping. So it's give you a very clear visual way to see where your design is going good or something may have a problem. So another thing is the what if analysis for the decoupling capacitors. So select, deselect, no matter you design the board has a footprint, so you can turn on and turn off, like I just said that, just look like those way, right? Or you actually can change the values right there in the list. So these are the values, you can change that if doing the different analysis. Another thing that I really want to point it out is something we call the virtual decoupling capacitors, which is sometimes you design the board, you didn't put enough decouplings there, or somewhere you haven't planned to do that yet. So actually you can do select that, add the virtual decoupling is just look like the red dots right there. So put it in there, it will be automatically added in the list of the decoupling capacitors. So you basically will see the effects immediately over the color mapping. So it's very handy. So you can find out if I do this, is that will be met my requirement or not. If not, then I may want to put other stuff, put in another places or different values or package size, all sorts of things, right? All right, so I actually will talk through a demo videos for you to see how the software goes. Okay, here you go. So this is a DDR4 PCIe combination board. So this is layer 1. These are all decoupling capacitors. We also have the layer 14 has the small decoupling under the ICs under the chips. So once you click analysis 2 button, or it comes out, it's automatically pair that accordingly for your definition for the power and the ground. Right? So this is the power bus views. So you can see clean a lot of things. So you can turn on, turn off different layers to see that. There also has a mark. Says is a result over there is violates the. Okay, let me hold on 1 second. I want to talk about it a little bit more. Okay, over here, there is a C target. You can do that. So I will show you later on in the demo there is the way to how to apply those things. Okay, so you click that decap. So these are all the list across these VDDQ and the DDR4 ground. So you can simulate that using select the different frequencies to see the Z21. So this is the 40 hertz. So basically it's a really low impedance. So 100 megahertz. So that it's a little bit higher, but if you, it's right there. If you look at the 200 megahertz, it actually violates the 1 ohm. So now we are going to check those, take off these, deselect those decaps to see how that results the changes. Yeah, go back to the PI distribution. You select the frequencies that you need it, and then you can displace this. Okay, so this is a 40 megahertz. Of course, is really good. 100. So you can see this is actually starting to have the red stuff is right there, right? Okay, so let's go back to the power bus again. So we can zoom in this so to see whether we wanted to add in a virtual decap to see how that goes. So first thing that we wanted to show you the spectrums. Yeah, just generate the impedance spectrum. It will be automatically put that point over there. So this is the point. Okay, here is the PDN impedance apply. Well, you can select that. So it will be automatically have the mask on it. So this is basically is a frequency range at the 1 point for the impedance. Okay, so now we are go back to the power bus view. We actually can add a virtual decaps right next to it. All right, now you can give the name. Yeah, then the values. Okay, so this is a picofarad. So 100,000 picofarad. So it's right there added. So if you have a ESR, ESL numbers, you also can do that. So just simulate it, and we go into the distribution. Yeah, select those three. Go to the put in over there, and we can see. Move this away. Click OK. Change it to, yeah. So now you can see, oops, sorry. So you can see over here, basically is the virtual decaps add-on, right? So you can see this is the whole thing is better, and also this one in this area is actually even better, right? So that's what the how virtual decoupling capacitor the works for your design to do the what if stuff. So we also sorry, I was on the back, sorry. Okay, here you go. So we gotta look at the spectrum again to see how that look like. The last time we see in the spectrum, we can compare to the previous one as well. Yeah, okay. Yeah, going to the spectrum, select that, you click. So this is this time is already had the virtual decaps. This is also add a mask for it. Now you actually can, yeah, this is a early one, so you can click back in the forth. You can see that the curve is changes, right? Yeah, so with the virtual decoupling capacitors is actually getting better. Okay, so this is what I have for the demo, short demos. So in conclusions, the mastering decoupling capacitors is a key to power delivery network excellence. So you design the power delivery is not only you strategically place the power and the ground plans, how you do this for the whole systems, but also sometimes, especially for very complex sports, the decoupling capacitor is very important for your PCB design to be stabilized. Simulation tools offers invaluable support for enabling design verification, debugging, and the what-if analysis. So whatever you designed in a PCB layout tools, if you have the simulation tools, you should use it to do the verification and debugging or what-if analysis to getting a best PCB designs out for your company, for your product. So consider 8,000 products to your partner for power integrity. So not only we provide our detailed simulation environment, but also this is very fast. It's using the parallel computing technology. It's usually few seconds simulation time for a board. Of course, so if you are really big board or very complicated, it may take minutes, but it's really fast. So when you're using that, you actually can be make sure your design will be, have with very robust designs as well. And the decoupling capacitor is the one of the things you really need to look at as well. Okay, that's it I have. Thank you, everyone.
Thank you very much, Lance. So everyone, I see that we have a couple of questions related to power integrity, and I'm very happy to share that we have Steve Sandler of Picotest here with us. Hi, Steve, you can unmute yourself and reply to the questions.
Yeah, hi, thanks for inviting me to come on, Lucy. So I see the two questions and I'll answer them for you briefly, but the first question is, how does two local decoupling capacitors versus one cap of double the value reduce overall impedance and improve filtering efficiency? Those two things to understand here. The first is that if we double the number of capacitors, we also paralleled their equivalent series inductances. So the two parallel capacitors are going to have lower ESL. For most of these capacitors, the ESR is a fixed minimum, a few milliohms. And so paralleling two capacitors will generally also result in lower ESR, not just lower ESL. And for the capacitance itself, using the same dielectric material, same size, same voltage rating, we could expect the same DC bias effect. But if they're not the same size or the same voltage or the same dielectric, two capacitors might have significantly different capacitance than one, even when we try to match those values. And so that's something that we need to be aware of. The second question was, what is the package size that's best for the decoupling capacitors closest to the integrated circuit? And this is a relatively simple question because the package size itself determines the equivalent series inductance. And as we get closer to the ASIC, what we want to do is minimize that ESL. That's one of the reasons that we have so many parallel capacitors to begin with. So in general, we want the physically smallest package size that we can get. And if we can fit them, wide geometry capacitors will be better than standard aspect ratio capacitors, only because they'll have lower inductance, and that's what we're after. On the other side of this, consider the fact that these capacitors then connect to the ASIC via the printed circuit board vias. The ASIC capacitors are typically on the back side of the board, and the ASIC is on the top side of the board. And that means that we have to get through the vias all the way from the back to the top of the board, meaning that the ESL of the capacitors may at that point become insignificant compared to the inductance of the via. And so at that point, we have to be really careful about the geometry of the vias and the physical location of the vias relative to the capacitor pads in order to minimize that inductance. But in general, what we want to try to do is we want to try to minimize the inductance, and we want to try to get the ESR of the decoupling capacitors to be close to the characteristic impedance of the ASIC package. That would be the onboard package capacitors and the package inductance itself leading up to the actual die. If the ESR were to get too low, then that will raise the Q of the internal package resonance, and the signals will actually get worse as we try to improve the capacitors. I have a couple of good papers with Heidi Barnes and Jack Carroll on that topic for anybody that's interested, but that's the answers to those two questions.
Thank you so much, Steve.
You
Thank
bet.
very much.
Okay, always happy to help you, Lucy.
Okay, bye.
Bye-bye, thanks.
Thank you, Steve.
You bet.
Okay, great. Lance, do you think you can take the next question?
Where's the question I can take?
It's in the Q&A section.
Here.
You have a question. How the size of the decaps affect the ESL?
Okay, so I would say the size for the decaps, ESL is the inductance. So if you have a package is fatter, that's the lower the ESL, right?
Okay, great. Thank you.
Yeah, one more question that I wanted to address here, Lucy. I see somebody asked the question about 3 different value capacitors.
Yeah.
And I do good article on that with Eric Boggin and Larry Smith called The Myth of Three Values or something like that. What we need to be careful of is we need to be careful that we don't resonate the PDN at different frequencies. There's also an article by Isvan Novak, the power integrity legend, and he showed what he considered to be multipole decoupling. And in multipole decoupling, he used a lot of different values in order to try to create something that looked like a noise pattern, but always had a peak that was below the target impedance. We talk about that a lot. We talked about that a lot in my rogue wave papers also. The trick is to try to keep that looking as flat as possible. The easiest way to do that is not to select, a selection of three different values of capacitors, but there is an exact solution for the decoupling capacitor at any location on the board, and that is that C is equal to L over R squared. So if we know the inductance of the power plane at a given location on the board, and we know the target impedance, we can calculate the exact capacitance required as C is equal to L over R squared. The second thing that's important to recognize about that is that the ESR of the capacitor has to be close to or equal to the target impedance. And if we can achieve that, then we can manage to get a flat impedance. Of course, the goal is to reduce the inductance in the process. And so this becomes an increasingly challenging effort as we need to parallel capacitors to get the inductance low enough, and yet we need to keep the ESR high enough that we don't end up just creating new resonances. That was actually the whole goal behind controlled ESR ceramic that was made by TDK, and those have all but disappeared from existence now because for some reason engineers think that the goal is to generate minimum ESR and not some specific value. And so it became a chicken and egg situation where the ESR controlled capacitors weren't in wide range usage, and that made them expensive. And because they were expensive, they were even less used. So the challenge is to come up with a capacitance that's equal to L over R squared that also has an ESR equal to the target impedance and a lower ESL than the inductance we're bypassing.
Mhm.
Okay, thank you very much.
You bet.
Well, it seems like we have one more question. Okay, who can take this one? Dilip?
Is this the one about the dielectrics?
Yeah.
Okay, so which dielectric is better for bypassing COG X5R, X7R? These are really, really different solutions, but let's start with X5R and X7R first. X5R is the highest density capacitor, so we can get the most capacitance into the smallest size. And that's really good if we need to come up with a large value of capacitor in a small package that has low ESL. That works really well. On the flip side, X5R isn't really great for temperature, and also it has the worst of the DC bias effects. And so we have to be careful when we choose X5R that we get the capacitance we're hoping for. It's pretty easy to get down to 50% of the label value or even lower. I've seen X5R capacitors that come in at about 30% of the value that they're listed as due to both the DC and AC bias. So X7R is a much more stable dielectric, but we can't quite get as high in capacitance. Still has a lot of AC and DC bias effect, but not as bad as X7R. When we get to COG is a very stable capacitor. They're really good for RF frequencies. In fact, almost all RF capacitors use COG. But on the flip side, what you're not able to do is get much capacitance in a package. So I go back to what I said previously, and that is that the decoupling capacitor requirement is C is equal to L over R squared. And so the question really becomes, what's the best dielectric that'll meet that requirement for the given capacitance? And that will help you determine that, that value. And I can see another question just popped up, and that is X2Y preferable? And well, the answer to that one is kind of simple also. X2Y capacitors are three-terminal capacitors, since they have much lower ESL than two-terminal capacitors. Couple of things to consider. One is that I said before that if we put these on the bottom side of the board for the ASIC, we still have to go through the vias. So getting the capacitor down to zero may not actually help, because the via inductance itself is going to more than make up for it. So you may not get as much of a reduction as you expected. Alternatively, you could use smaller capacitors and just put them end to end, and it would look just like an X2Y capacitor. And if you made them wide geometry capacitors, they would be even better. So I guess the answer is that X2Y is a three-terminal capacitor that's designed to provide lower ESL by providing a shorter electrical length from each end of the device to the middle pad. And given that, if the vias don't add more inductance than the capacitor does, you might still find it beneficial to use X2Y capacitors. They just take a lot of space. Okay, yeah, I do see another capacitor came up about X8R. You know, X5R, X7R, X7S and T, X8R, these are all similar dielectrics. And the question is, how stable are they over temperature? And how stable are they over DC and AC bias? And so those are the only real concerns. I can tell you, I've seen a lot of higher power boards that are using X5R capacitors. And you can actually watch the decoupling change as the board warms up. And we've recorded changes in those capacitors up to about 50%, just due to the printed circuit board warming up. So hopefully that answers the question.
Mhm.
Okay, and there was one over. Oh. Yeah, there's one last question by Syed.
So let's go back to this, because I already sort of answered this. The question is, what is the bump? The bump is the resonance of an inductance and a capacitance that has a Q that's greater than 1. That's the cause of the bump. If we look at the rising side of the bump on the left-hand side at 260 kilohertz, that's the inductance. And if we look at the falling edge of that bump, well, that's the capacitance. So how would you reduce that bump? C is equal to L over R squared. And so what that means is that there's insufficient capacitance to absorb that inductor. What you really want to do is to make sure that the ESR matches the target impedance and set the capacitance such that C is equal to L over R squared. And then you won't have a bump.
Okay, great. Thank you so much.
Okay. All right, guys, I gotta go, but I'm happy I was able to answer those questions for you.
Okay, great. Thank you so much, Steve. And thank you so much, Lance and Zukan, for doing this webinar with us. Thank you, everyone, for attending. I will send you the recording and slides later today.
All right. Thank you. Thank you, Steve.
Thank you, Lucy.
Bye.
You bet, guys. Bye-bye.
Bye.
Bye.